In the nanomechanics and optomechanics team at the Laboratory for Photonics and Quantum Measurements, we engineer strong interactions between light and motion. We embed nanomechanical resonators in optical cavities, where the motion of the mechanical resonator leads to a phase shift on the light coming out of the cavity, and the light acts on the mechanical resonator through radiation pressure. This allows us to measure and control the position of the mechanical resonator at the quantum level. An important part of our work is to isolate the motion of the mechanical resonator from the environment. We therefore develop nanomechanical resonators with extremely high quality factors, reaching the billions. These devices are fabricated in the EPFL Nanofabrication Facility, CMI, and we characterize our devices using optical interferometers in ultra-high vacuum chambers, both at room temperature and cryogenic temperature.
Welcome to the circuit team. Here, we are interested in quantum control of motion of a tiny superconducting membrane and microwave signals in superconducting circuits. Generally speaking, to realize quantum control by electromagnetic fields, the key element is nonlinearities. In our team, we have two of the most successful nonlinearities for quantum technologies, which are brought by the radiation pressure force of microwaves on motion and Josephson junctions. We are looking forward to seeing what happens when we combine them in a single device. This is our laboratory. We have two dilation fridges that reach about 10 millikelvin at a base temperature. That is important for our devices to go to the quantum regime. And we have a lot of microwave instruments to control and measure our devices in the quantum limit.
LiDAR stands for Light Detection and Ranging. We apply microresonator frequency comms technology to investigate novel concepts of LiDAR. It all starts with a small laser on the left coupled to a chip. The laser pumps one of the microresonators and the frequency comp is generated. The multitude of the frequency lines is sent to the free space with diffraction optics illuminating the target area. In the following demo, our LiDAR shines at Anton. His velocity is determined by the spread of the varying frequency spikes, and the range corresponds to their mean. Our LiDAR achieves centimeter-level precision while operating at hundreds of meters.
Microcomb is a shorthand for microresonator-based frequency combs, fast optical spectra formed from circulating pulses inside a resonator, driven by some pump laser. From a microresonator, the spectrum can be seen as an array of laser lines or comb teeth, and can be thought of as an energy ruler. Accordingly, they can be employed in applications as diverse as biological and chemical sensing, telecommunications, and astronomy. In our lab, the microresonator is a silicon nitride waveguide platform fabricated on microchip. In this driven nonlinear dynamical system, through a balance between the Kerr nonlinearity, optical dispersion, and gain and loss, solitons can be formed. Solitons are the most fundamental stable structures of light that can exist in driven optical systems. Through numerical modeling, we can simulate the complex formation behavior of such objects and design our microresonators accordingly. Here is our microcomb lab space, where dreams become reality. The centerpiece is the enclosure housing our microchip resonator, connected by optical fibers. To generate a soliton microcomb, we turn on the laser, then engage any electro-optics to boost our input pump, and then carefully tune our laser into resonance. Doing this generates a soliton microcomb.